Hello, and welcome back to the Calculus 1 playlist. In today's video, we're going to be starting our discussion on mathematical induction. Essentially, mathematical induction is a way to prove things for discrete numbers or natural numbers. So we're able to prove conditional statements or statements pertaining to natural numbers. So we'll be going over the theory behind it, the steps that are required, and then several examples. And this is because it can be kind of a confusing topic for first-year students or discrete math students to undertake. But throughout practice or just through understanding what's going on, I hope to give you guys a better way of understanding this topic. So let's begin. And to start, I'd like to give you some kind of introduction discussion. So let's say we have these marbles. We have all these marbles lined up as such. Okay, so we know that this is the first marble, second marble, third marble, and we go, let's call this the kth marble, k plus 1 marble, and then we keep going, then we have n minus 1 and nth marble. So these are all marbles, and they're all in a straight line. So let's say I hit the first marble, and then in doing that, that hits the second marble. And the momentum from this impact causes it to hit the third marble. I want to see if it hits all the marbles in my set of n marbles. So we have n marbles in the entire set. Well, then we can say if it hits the third marble and keeps going, would the one before the kth marble hit it? And then it hits the kth plus 1 marble. And then we can keep going, and it hits the n minus 1 and nth marble. Well, let's say we want to prove a conditional. It would be really draining to prove for every single case. It would be hard to prove for if we want to say, okay, we want to know if it hits every single marble. It'd be kind of boring to check, okay, if we hit the second marble, then we move on to the third, we check the third marble, then we go fourth marble, fifth marble, sixth marble, so on and so forth, till we go to the k plus 1, n minus 1, n. So we have all these different marbles, and it would be very draining to check every single case. So what mathematical induction does is it provides a way to check whether we've hit all the marbles in our series. So if it is true, if a statement is true for all natural numbers. So if we've hit up to a certain point, then we can assume for the rest that we're hitting all the marbles. So induction or mathematical induction is a method to prove statements true for natural numbers. And if you recall, a natural number is just a number greater than 0. So it's all the whole numbers bigger than 0. So we can use induction for sequences. We can use induction for summations and inequalities. So we can use this kind of method of checking all our numbers in a statement with the following sequences, summations, and inequalities. But what do we do? Like, how does this method actually works? Well, the method involves 3 steps. So your first is your base case. Base case. So what you do is you prove the statement true for the first case. So essentially, if we looked at our marbles instance, we look to see if we hit the first marble, will that hit the second one? And if that is true, then we proved the base case. It works for the first marble. Then, the second one, we have our induction hypothesis. I'm just going to note it as I.H. And in this case, we assume the statement is true for some arbitrary number n is equal to k. Right, so if we go back to our marbles again, we don't know necessarily if it's true. And just as I referred to in the conditional statements video, the material conditional statement in the last video, it doesn't have to be true. So with step 2, and it gets a little bit tricky, and you'll see when we go over examples what I mean by that. Okay, we proved that for the base case it works, but for the induction hypothesis, we just assume that for the kth term that it hits, right? You see, I don't have a ball in front of it. I don't know if the ball hits or not, but we're just going to assume that the ball hits, the marble hits the kth marble, causing it to go forward. So we're going to assume that it's true, right? So the third step then is the induction step. And I'll refer to it as just IS. It's a shorthand notation. Prove the statement is true for n is equal to k plus 1, right? So if we're looking back at the marbles again, with the last step, the induction hypothesis, we just assumed that it hits the kth one, and now we need to assume that whether this k marble will hit the k plus 1 marble. So we need to prove that this is true. So the induction hypothesis is an assumption, and using that assumption from the induction hypothesis, we're able to prove if this works for the k plus 1 term. And if this is the case, so if 1 and 3 are proven true, statement is true for all n. And I can represent for all as this shorthand, as I'll do for the rest of the video. But essentially, we're saying that if we can prove that the base case holds and the induction step holds, then we can say that this works for all n. We can go all the way to the nth marble. And the reason why is because we can say this is our set n, or everything inside. Well, k is just a smaller subset, right? But since n is, since we proved for k, we can say then for all n, this holds. And within k, we have our base case. So we said, okay, it held for the base case, and it held within this certain interval n, within the certain interval k, sorry. Then we'll just assume that it holds for all of n, right? So this is kind of the way we do it. And notice, we're not proving anything with the induction hypothesis step 2. We're proving with only the base case and the induction step. The induction hypothesis is an assumption, and we use that assumption in our induction step. So using the induction hypothesis, we should be able to prove the induction step. So that might seem a little bit tricky right now, but as we go through some examples, I think you'll see what I'm doing and you see what I mean, and I'll kind of go step by step to demonstrate what we're doing. So let's look at some examples. So example 1. Prove that we'll have this sum, 1 squared plus 2 squared plus 3 squared plus going all the way till n squared is equal to n plus 1, and 2n plus 1, all divided by 6, for all, remember this sign means for all n, where n is an element of the natural numbers. Perfect. So how do we go about doing this? And we want to do this with induction. Let me clarify, with induction. We need to prove this with induction. But yeah, how do we go about doing this? How do we actually solve this? Well, first we check the base case. So base case. Well, the base case is just n is equal to 1, because we're looking at the natural numbers, and natural numbers are n greater than 0. Well, if n is equal to 1, then we have 1 squared is equal to 1, 1 plus 1, 2, 1 plus 1, all over 6. We just plug in n is equal to 1 in our statements. And, well, it turns out 1 squared is equal to 1. And we have 1 multiplied by 2 multiplied by 3 all over 6. Well, this is just 1 is equal to 1. 2 times 3 is 6. 6 divided by 6 is 1. So we've proved that the left-hand side is equal to the right-hand side for our base case. So we're done with that part. Fairly straightforward. Now the induction hypothesis, and I'll write I dot H. Again, assume, because again, the induction hypothesis is just an assumption that we say that n is equal to k, some arbitrary number n is equal to k. So assume that we have 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared is equal to k plus 1, 2k plus 1, all over 6. Great, and that's it. That's it for our induction hypothesis. And we can say for all n is equal to k, where n is greater than 0 since it's a natural number. So now we need to go through our induction step, I dot S. So in our induction step, we kind of have to use this result in our induction hypothesis to prove it works for the next term, the kth plus 1 term. So let's write down what we need to prove. Prove 1 squared plus 2 squared plus 3 squared plus dot 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 plus k plus 1 squared is equal to, and this becomes k plus 1. We just replace everywhere we have with a k plus 1. Then inside here would be k plus 2, and here would be 2 k plus 1 all over 6. Great. So what do? Well, we need to incorporate our induction hypothesis in some matter. So let's write our sum with the kth term, right? Let's write our induction step sum with the kth term involved. So we have 1 squared plus 2 squared plus 3 squared plus the term before the k plus 1 term. That's just the kth term, right? K squared plus k plus 1 squared, and that's going to equal to k plus 1, k plus 2, and this term is right here. We can just expand and simplify 2k plus 3, and that's all divided by 6. Well, when we look at this term, if we analyze it closely, we said using our induction hypothesis that, let me highlight it. We said that term is equivalent to this expression, right? We assumed that. So if we're assuming that this is the case, then we can plug in this into our sequence right here. So I'll plug in k of k plus 1 of 2k plus 1 all divided by 6 plus k plus 1 squared is equal to our left-hand side, or our right-hand side, k plus 2, 2k plus 3 all over 6. Again, all I did is I used the fact that we assumed that 1 squared plus 2 squared plus 3 squared plus all the numbers added up till k squared is equal to k multiplied by k plus 1 multiplied by 2k plus 1 divided by 6. And because we have that in this expression right here, we can just go ahead and replace that. Now, all we have to do is use simple algebra to simplify. Great, so we can go k plus 1, 2k plus 1, plus 6k plus 1 squared all over 6, just bringing everything under one common denominator. And then I'll just write dot, 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 but we know dot, dot, dot represents this, k plus 1, k plus 2, 2k plus 3 divided by 6. And then what can we do to this? We can factor out a k plus 1, right? So we can go k plus 1. And doing that, that leaves us with k, 2k plus 1, plus 6, k plus 1, all over 6 is equal to dot, dot, dot. Then going on, we can expand the terms inside this right here. So we'll go k plus 1, and that gives us 2k squared plus k plus 6k plus 6 all over 6 is equal to dot, dot, dot. Great. Now let's factor inside that big brackets, we can see that that is, so straight away 2k squared plus 7k plus 6, and then we can factor this in the next step. This step right here, we can see that this comes k plus 1, and factoring two numbers that multiply to 12 and add to 7, that is 3 and 4. So we can have 2k squared plus 3k, and that'd be here, and 4k plus 6 all over 6. And I'll copy this value here now so that we can have it as a reference. Perfect. Well, then if we're factoring these two, we can pull out, so x plus 1. In the first term, we can pull out a k. So we'll have k, and that gives us 2k plus 3. And in the second term, we can pull out a 2, and that gives us 2k plus 3 all over 6. And that's equal to k plus 1, k plus 2, 2k plus 3, all over 6. And you can see if we just factor out 2k plus 3, we have our left-hand side equal to our right-hand side, right? We'll have k plus 1, k plus 2, 2k plus 3, all over 6 is equal to k plus 1, k plus 2, 2k plus 3, all over 6, right? So then we can just say then the left-hand side is equal to right-hand side. So we proved this true with induction, right? So again, to highlight what we did here, we proved for the base case and the left-hand side is equal to the right-hand side. Then we assumed that this, I guess, summation is true, or this statement is true for some arbitrary value k. And using that assumption, we were able to prove that it's true for the very next term. And because that's the case, we can say then, okay, it's true for all n. And that is mathematical induction. That's how you work it. And so I'll go through more problems like this. They're going to get some increase in complexity. But again, this is the general procedure. You prove for the base case, then you make an assumption for some value k. And then using that assumption, you prove it for the very next term, k plus 1. So let's go to the next example. So for the next example, we'll have example 2. Prove that, and we'll have the following statement. It'll be 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed plus, we go 1 over 2 to the n, and that needs to equal to 1 minus 1 over 2 raised to the n. And this is true for all n, where n is an element of the natural numbers, meaning n greater than 0. Cool. So again, the first step is to prove that this works for the base case. So n is equal to 1. So we have 1/2 raised to 1 is equal to 1 minus 1/2 raised to 1. Well, this is 1/2, and we can clearly see that the other side is 1/2. So this is equal to true. Left-hand side is equal to right-hand side. And I'll go a little bit quicker for these next examples, just so we don't spend too much time. But again, I'll still explain my steps. So the next one is to do the induction hypothesis, meaning we are assuming 1/2 plus 1 over 2 squared plus 1 over 2 cubed plus 1, let me go like that, plus dot dot dot, plus 1 over 2k is equal to 1 minus 1 over 2k for all n is equal to k and n is greater than 0. Great, now we got to do our induction step, I dot s. Prove that 1/2 plus 1 over 2 squared plus 1 over 2 cubed plus dot dot dot. Let me fix that, sorry. 1 plus 1 over 2k plus 1 is equal to 1 minus 1 over 2k plus 1. So again, we're going to need to use our induction hypothesis somehow. So let's write the term before the kth plus 1 on our summation. 1 plus 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed plus dot 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 plus 1 over 2 to the k plus 1 over 2 to the kth plus 1 term is equal to 1 minus 1 over 2k plus 1. Again, we can see, just like in the previous example, that we've said that this is our induction hypothesis, that we're assuming that what this term represents is equal to 1 minus 1/2 raised to the kth power. So we can say that this is equal to 1 minus 1 over 2k plus 1/2 2k plus 1, and that needs to equal to 1 minus 1 over 2k plus 1. And now on the left-hand side here, let's kind of represent the top and the bottom with the 2k plus 1 for this term. So what do I mean by that? 1 minus, well, if we multiply the top and bottom by 2, we'll have it like this, plus 1 over 2k plus 1, and that's equal to 1 minus 1 over 2k plus 1. Well, this is just 1 over plus 2. I'll write it as such, because we can write them under the same denominator, right? This is equivalent to 2k plus 1. Well, we know that we can just kind of solve this and get into this form. So again, we kind of wrote everything under one common denominator, and then simplifying our terms, we ended up with the left-hand side equivalent to the right-hand side. So left-hand side is equivalent to right-hand side. Therefore, we prove this by induction. So again, just to highlight, we used our induction hypothesis to prove our induction step. And then just by some simple algebraic manipulation, we're able to prove our induction step. Great, let's move on to the next example. So for the next example, example 3, let's say we're going to work with an inequality in this case. So it'll follow a similar procedure, but again, we're going to be using an inequality. So prove that 3n is less than n plus 1 factorial for all n greater than 4 by induction. So the first step, as always, is to prove the base case. So for this, n is equal to 4, since we're bounded from n being greater than or equal to 4. So 3 raised to 4 has to be less than 4 plus 1 factorial. Well, on this side, 3 raised to 4 is 9 squared multiplied, or so yeah, 3 raised to 4 is 9 squared. 9 squared is 81, so we have 81. And then on this side, this is 5 factorial. And recall, 5 factorial is just 5 times 4 times 3 times 2 times 1. 5 times 4 is 20, and you multiply that by 3 is 60. Multiplying that by 2, you get 120. So 5 factorial is equal to 120. So 81 needs to be less than 120, which is the case. So we have this being true. Great. So now we need our induction hypothesis. So assume that 3k is going to be less than k plus 1 factorial. And this is for all n is equal to k and n is greater than or equal to 4. Great. And now our last step is the induction step. So we need to use the induction hypothesis to somehow prove that 3k plus 1 is going to be less than k plus 2 factorial. So we want to prove that. So let's start with writing out our inequality of our induction hypothesis. So 3k less than k plus 1 factorial. So let's multiply both sides by k plus 2. And you might think this is kind of like arbitrary, like, okay, why would you do that? But again, we want to prove that for the next term, this is true. So in doing that, we'll have our right-hand side of the inequality similar to the induction step proof. So if we multiply both sides by k plus 2, we'll be left with 3k, and then I'll have k plus 2, less than k plus 2, and this is k plus 1 factorial. And you recall, if you want to rewrite something as a factorial, we can say if we have the very next term and the factorial of the term previous to it, we can just write that as the factorial of the entire term. So to demonstrate that, that just represents this, x plus 2 factorial. Perfect. Okay, now that we have the right-hand side down, we need to analyze to somehow prove this. Well, we can say something that you might note is this is just like that. That 3 raised to k plus 1 is equal to 3 multiplied by 3k, just by rules of exponents, right? But notice here, we have this coefficient here and this coefficient here. So if we can relate k plus 2 to 3, we might be able to work with this. So no, we said that n is equal to k and n must be greater than 4. So therefore, k must be greater than or equal to 4. And k plus 2 must also be greater than, therefore k plus 2 must be greater than or equal to 6. Well, inherently, that means that k plus 2 is greater than or equal to 3, right? And so we can say then that 3k is going to be less than, and I'll put it like that, less than or equal to 3k, k plus 2. I'll make it a bit better for you. Let's put the 3k, k plus 2. Just from the fact that we know that this term has to be bigger than 6 and this term is 3. So we know that if since the coefficients are what's remaining, you could cancel 3k, k plus 2 has to be bigger than 3. So in doing that, we can write the following inequality. We can then write 3 raised to k is going to be less than or equal to, and we'll have our middle term, 3k, k plus 2, and we'll have this term, k plus 2 factorial. And there should not be an inequality, equal sign below the inequality. Sorry about that. Okay, well then we can just relate these two. We can write a new inequality saying 3k is less than k plus 2 factorial, just by knowing the fact that this is larger than this, which is larger than this term. And we can rewrite this as 3k plus 1 is going to be less than k plus 2 factorial. And again, this is proven. So proven by induction. This is what we wanted to prove, recall. Like this right here, that for the very next term of the induction hypothesis, we're going to find that it is less than 3k plus 1 is less than k plus 2 factorial. So we've proven this. Great, let's move on to the next example. So in this one, it won't be too difficult. In our example 4, this one won't be too difficult. So prove, and we'll have summation n, r is equal to 1 of r is equal to n plus 1 all over 2 for all n greater than 0. Perfect. So what does this summation look like? And we have to do this by induction again. So what does this summation actually look like? Let's say n is some arbitrary number. Well, it turns out that's just 1 plus 2 plus 3 ... plus, and we're going all the way to n. And we're saying that that is just equal to n plus 1 all over 2. Great, so first we need to prove the base case works. So for the base case, we'll have 1 is equal to 1 plus 1 all over 2. Well, that's just equal to 1 is equal to 2 over 2, and we know that this is equivalent to 1 is equal to 1. Left-hand side is equal to right-hand side, so we're good. Now we need to do our induction step, or our induction hypothesis, sorry. So I dot h. And we need to say that 1 plus 2 plus 3 plus dot 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 plus k is equal to k plus 1 all over 2. Perfect. And last but not least, we need to go through our induction step. Induction step I dot s. And again, we'll include 1 plus 2 plus 3 plus dot 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 plus the kth plus 1 term. And this side becomes k plus 1, k plus 2, all equal to 2. Great. Recall, and I'll put brackets around this, we can write the summation on this side as the following. We'll have k plus 1, k plus 2, divided by 2. And that from our induction hypothesis, we have this 1 plus 2 plus 3 plus all the way to k is equivalent to this term. And we have that represented right here. So we can replace that saying k plus 1 all over 2 is equal to, oh, sorry, I forgot to add another k plus 1, plus k plus 1 is equal to k plus 1, k plus 2. Well, adding a common denominator of k plus 1 plus 2, k plus 1 all over 2 is equal to k plus 1, k plus 2 all over 2. And factoring out k plus 1 on the left-hand side, we're left with k plus 1, k plus 2 all over 2 is equal to k plus 1, k plus 2 all over 2. We have our left-hand side is equal to right-hand side. So it is proved by induction. Fairly straightforward. And as you can see, majority of this is algebraic manipulation to get the sequence or the summation or whatever it is that you're trying to prove in the right format such that you can solve. Perfect. Next question. So for the next problem, we have example 5. States that prove the Bernoulli's inequality using induction. And the inequality pretty much states 1 plus x greater than or raised to n has to be greater than or equal to 1 plus nx. And in this case, n is an element of, or sorry, let's just write it like this. N must be greater than or equal to 0, and x has to be greater than or equal to -1. Perfect. Well, we start with our base case. And for our base case, again, we'll use 0, n is equal to 0, since that's where we can start. And we'll have 1 plus x raised to 0 greater than or equal to 1 plus 0x. Well, on the left-hand side, that just becomes 1, since anything raised to 0 is 1. And on the right-hand side, we're just left with 1. And in this case, is 1 greater than or equal to 1? That is certainly true, so our base case holds. Next, we need to do the induction hypothesis. So 1 plus x raised to k has to be greater than or equal to 1 plus kx. And this is for all n greater than or equal to 0 and x greater than or equal to -1. And in this case, we'll now write the induction step where 1 plus x raised to k plus 1 has to be greater than or equal to 1 plus k plus 1x. Perfect. So we're going to work with our induction hypothesis to start. So let's write that out. Not k. That will be x raised to k greater than or equal to 1 plus kx. So what we'll do, and it might seem arbitrary at first, is multiply both sides by 1 plus x. So we'll go 1 plus x, and we'll have 1 plus xk greater than or equal to 1 plus kx, 1 plus x. And the reason why we did that is just so that we can write the left-hand side similar to the induction step, such as that. So when we do that, we'll be left with 1 plus x raised to k plus 1, and that'll be greater than or equal to what we have on this right-hand side, and that is 1 plus, 1 plus x, 1 plus kx. I just switched the sides of the of our two, I guess, bracket equation, two bracket statements on the right-hand side. So now we're going to expand that right-hand side. So 1 plus x, k plus 1 greater than or equal to, well, this becomes 1, this becomes plus kx, this becomes x, and this becomes kx squared. And if you notice, we'll rewrite the left-hand side first. If you notice, well, then this right here can be factored out with an x, can do 1 plus k plus 1x plus kx squared. And look, this is the exact same as right here. These two portions. But we want to check what this is. Well, we know just from our conditions that since n is equal to k, and I forgot to write that here, n is equal to k, we know that this is going to be either 0 or bigger, and x squared is always going to be positive. It's going to be a bare minimum of 0. So this term is going to be always, since k is greater than or equal to 0 and x is greater than or equal to 0, then this term kx squared, or x squared, sorry, is always going to be greater than or equal to 0. That's just given. So then we can write out this inequality then, that 1 plus k plus 1 x plus kx squared has to be bigger than or equal to 1 plus k plus 1 x plus k, or sorry, just like that. And that is just since the fact that this term is either 0 or positive, and these two terms are the same. Great, so then we can also write then over here, can continue our inequality, 1 over x k plus 1. Just bring down this, we can add that statement to this inequality. And then combining these two inequalities, we can get 1 plus x raised to k plus 1 is greater than or equal to 1 plus k plus 1x. And this is exactly what we wanted to prove. This is the same as the induction step. This is what we were looking to prove, so we proved it. Therefore, Bernoulli's inequality proved by induction. Perfect. So again, not too difficult. We used our induction step, our induction hypothesis to prove our induction step. Great. So let's look at one final example for today. So for this example, I want to show that 10 raised to 2n minus 1 minus 3 2n minus 1 is divisible by 7 for all n greater than 0. Okay, so let's try the base case. We're going to do this by induction. So let's analyze the base case. Well, in the base case, we have n is equal to 1. And when we do that, we have 10 raised to 2 multiplied by 1 minus 3 raised to, 2, 1 minus 1. Well, this is just equal to, I'll put it on below. This is just equivalent to 10 minus 3, which is equal to 7. Well, 7 is certainly divisible by 7, so we can say that holds. Then we'll write our induction hypothesis, and this is important. So our induction hypothesis, so now we assume that 10 raised to 2n minus 1 minus 3 2n minus 1 is divisible by 7. I'm not saying that it is. We don't know if it is, but we're just going to assume that it is divisible by 7 for all n is equal to k and n is greater than, not equal to, greater than 0. Perfect. So now that we've assumed that this is divisible by 7, and I need to write this as a k, Sorry about that. This needs to be 2k minus 1. 2k minus 1 is divisible by 7 for all n is equal to k. So then in our induction hypothesis, or our induction step, we need to prove that 10 2k plus 1 minus 1 minus 3 2k plus 1 minus 1 is divisible by 7. So how do we do that? Well, we'll start by just looking at this induction step, what we need to prove. Well, we can write this as 10 2k plus 2 minus 1 minus 3 2k plus 2 minus 1 just by expanding the exponents. And we can also write this like this. We can take out that 2. So normally you would have simplified the exponent, but instead we can kind of rewrite it as such. And you'll see why I'm doing it like this shortly. Right, so we have it similar to our induction hypothesis. And remember, we said our induction hypothesis is divisible by 7. Great. So now we have this 10 squared multiplied by 10, 2k minus 1, minus 3 squared, multiplied by 3, 2k minus 1. Well, let's simplify as such. And multiply by 3, 2k minus 1. And let's rewrite 100 as 91 plus 9. 91 plus 9. And I'll go like this just to clarify, going step by step. 91 plus 9. And this is so that we can factor out that 9 from both, from the 10 2k minus 1 and the 3 2k minus 1. So let's expand this now. So you'll be left with 91 multiplied by 10 2k minus 1, and as well 9 10 2k minus 1 minus 9 times 3 2k minus 1. Well, we can what's called factor out that 9. So we'll be left with 91 times 10 2k minus 1 plus 9 10 2k minus 1 minus 3 2k minus 1. Perfect. But recall, from the induction hypothesis, we assume that this is divisible by 7. This is divisible by 7. And note, if something is divisible by a number, so let's say we have this coefficient being a and this coefficient being b. So this term in brackets is b. So if we have a my b, and it gives it, and that's it's a product of something. Well, if we say that b is divisible by 7 into an integer number, then we can say any integer value of a multiplied by b is also going to be divisible by 7. So this will be divisible by 7 since this is divisible by 7 and multiplied by that coefficient a. So we know that this term right here is divisible, that's a percentage, that is divisible by 7. And likewise, okay, well, is 10 2k minus 1 divisible by 7? We don't know. But we can see that 91 is divisible by 7, right? So we can just, by inspection, we know that 91 is divisible by 7, but I'll show you. We'll have 1 here, and this is 9 carry the 7, sorry. 2, 1, 21, that's 3. So we know that 91 divided by 7 is 13. So this term, since this is divisible by 7, then this entire term is divisible by 7, and we're done. That's it. And again, the main reason why we're able to prove this is because we used this assumption, the induction hypothesis, that since this term is divisible by 7, we assumed that, then we could say that this is divisible by 7. And that's how we're able to prove things with induction. So that's going to be all for this video. The topic of induction is fairly complex and fairly challenging. So the main thing is to practice. Hone your skills with algebra, be able to manipulate equations and statements to get them in the forms that you'd like. And that's your best way to doing well with induction, either in calculus or discrete math or however course you're taking it with. So if you enjoyed, please feel free to leave a like, share, subscribe, and leave your comments if you have any questions, and we'll be continuing our topics in the next video.